Okay, so yeah, so I think we are already late. Let's start our meeting. Yeah, so I'm Zia Krishnasan Avatar. I will be the TA for this NPTEL course on variation calculus and its applications, control theory, and nanomechanics. This is the first tutorial session which starts today. We'll be discussing the first and second weeks of the course. And I would be discussing mainly about the basics of optimization principles and the variational calculus and the necessary sufficient conditions for optimization, the the various and the basics of variational calculus, as well as Euler and how to derive Euler Lagrange equations, general and further followed by generalized Euler Lagrange equations. And then I would follow it up with several solved examples in for every class of problems that we have here in all these areas that I would be reviewing. Okay, so let me first begin with the basics of optimization. And we first start with the single variable optimization, which is in which we are given a function for which we need to determine at which points it maxima lies or at which point does its minima occur. And the necessary conditions for determining the extrema for such problems are by equating the first derivative of the function to zero, and and we denote the extremal points as x star. And the sufficient conditions to determine whether these points are local maximum or local minimum are given by the second derivative of the function at those points. Now, it may happen sometimes uh, that our second derivative becomes zero. In this case, we need to resort to finding derivatives at higher order derivatives, and then evaluate it, uh, and then seek for those derivatives which are non-zero. And based on it, if say the first higher order derivative to be non-zero is an even integer, then we and it's greater than zero, then we call it as minimum. Uh, and and if the highest the derivative, even I mean if it's always zero, then it becomes look, and then we cannot conclude anything about the extrema of the whether it's local minimum or local maximum. Okay. Now let's move on to finding the discussing about the multiple variable optimization. In this case, we are given a function in n variables, which are x1 x2 till xn. The necessary condition for extrema is given by and equating grad of a vector to be zero. And in this case, grad operator here simply implies that we are partially differentiating every component of, I mean, f with every component, which is in this case, which are variables x1 and x2, and equating all this system of equations to zero. The solution to the system of equation is x star, which is local, which are the extrema of the problem. But as we clearly know from the previous slide, that it doesn't mean that just having derivative, I mean the gradient of function to be zero doesn't imply whether it's minimum or maximum. So we need to resort to sufficient conditions to uh, to to draw some conclusions from about the extreme. So the sufficient conditions are first, in order to do that, first we determine the Hessian matrix of the system. And the Hessian matrix system is a matrix in which every components are uh, second derivatives of f with respect to the optimization variables, which are x1, x2, and x till xn. Now to determine whether our local whether this is whether the extremum is a local minimum, uh, we need to determine all the eigenvalues of h. If all the eigenvalues of h are greater than 0, that it implies that the extrema is a local minimum. However, if all the eigenvalues of h is less than 0, then it implies that our extremum is a local maximum. Okay, with this short review on optimization, let us now briefly talk about variational calculus. Now, variational calculus is essentially optimization in function space. In this case, here, um, uh, when compared against the multivariate and single variable optimization that we had discussed, this is more sophisticated in the sense that here the here our aim is to determine an extreme which happens to be a function. So essentially this becomes an optimization in function space. Now here we start with functional. So here the functional is what we need to extremize, and the function for us here, we have uh, it's given by this expression here that jy is equal to uh, integral from x1 to x2 f of x f y prime dx. And now we need to extremize jy with respect to y, and this leads us to Euler-Lagrange equations, which we have the equations here. Now it so happens that uh, in many problems we do find that our functional doesn't just depend on the function and its first derivative. We also have a function. We can even have higher derivatives in the functional. So what we do is then we obtain something known as, when we extremize this functional here, then this leads us to generalized Euler-Lagrange equations, and this is given by the expression here. We have -1 to the power n dn by dx and del f del y n plus -1 and n minus 1 dn minus 1 by dx minus del f by del y n minus 1 plus till then plus f del f by del y is equal to 0. Okay, now let me begin with us with solid examples in for all the things that we have reviewed just now. But before that, let me start with solution of ODEs, because essentially um, till I mean till now in week 1 and week 2 we have been dealing with ODEs. So let's first let's just first review how do we solve an ODE. So the first problem here is y double prime plus 4y is equal to 0, which is subject to boundary conditions y0 is equal to 0, y1 is equal to 1. This, as we see, is a second order ODE. It's linear and homogeneous. Homogeneous, it simply implies that the term on the right hand side is 0, and all the terms in this differential equation consist of y. For this, what we do is, in order to solve the problem, let's assume a solution of the form yx is equal to e to the power lambda x, where lambda is an element of y, and we differentiate with respect to x to get y prime of x is equal to lambda e to the power lambda x, y double prime of x is equal to lambda square e to the power lambda x. Then we substitute the expressions in y double prime plus 4y is equal to 0, such that we have lambda square e to the power lambda x plus 4 e to the power lambda x is equal to 0. Then we factor all the terms, factor out e to the power lambda x is equal to 0. And what we see is, we know that e to the power lambda x is not zero, and it can, and since both lambda and x are finite, this term won't be equal to zero. So this simply leads us to lambda square plus 4 is equal to 0. This implies that lambda is equal to plus minus 2i. Okay, and the general solution to this problem is yx is equal to a e to the power 2ix plus b e to the power minus 2ix. We use the Euler's formula, which is e to the power 2ix is equal to cosine 2x plus I sine 2x. Similarly, for e to the power minus 2x. So it's plus b cosine 2x minus I sine 2x. By some algebraic manipulation such that we make a plus b uh, is equal to c1, and I of a minus b, that becomes c2, and this so that we have uh, an expression in terms of sines and cosines. Now what we do is let's put the boundary conditions. So we are given two boundary conditions. One is y0 at 0 is equal to 0, and the second is y1 is equal to 1. So this implies that after putting the first boundary condition, this leaves us c1 is equal to 0. After putting the second boundary condition, this simply means that c2 sine 2 is equal to 1. This implies that c2 is equal to 1 by sine 2. And then yeah, after putting all the values of the constants, we have yx is equal to 1 by sine 2, sine twice of x. Okay, now let's go to a different problem. And we have this problem which is which by its very appearance it's a fourth order and linear, because all there is all the terms present in the equation have doesn't have all the terms are linear in y, which means that um, the exponent of 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 y in every term is 1. It's also homogeneous because there is no term which doesn't contain y, and uh, and it's an ODE obviously. Okay, so what we do is let's assume a solution of the form yx is equal to pi lambda x, and similar to what we had carried out in the previous question, and then y prime of x with their differentiate with respect to x. This gives us y prime is equal to lambda e to pi lambda x, and and the fourth derivative becomes lambda to the power 4 e to power lambda x. Upon substituting these expressions in y for minus 6, fourth derivative of y minus 16, y is equal to 0, is equal to 0, then we have lambda 4 e to the power lambda x minus 16 is equal to 0. Okay, okay, so what we do is we factor out e to the power lambda x, and help from, and similar to the previous argument on the previous slide, and e to lambda 4 minus 16 is equal to 0. And then we'll factorize it in terms of this one, and this we'll get two sets of the roots are plus minus 2 plus minus 2. Okay, okay, now the general solution is equation is a to the power 2x plus b e to the power minus 2x plus c to the power I 2x plus d to the power minus 2x. Okay, and then what we do is let's express, there's one form of expressing the solution. Then what we do is, why cannot we use tangent hyperbolic or hyperbolic function, so to speak, hyperbolic trigonometric function, which is sine hyperbolic, cosine hyperbolic. Okay. So likewise, we use express we use the Euler's formula to do this one, to expand e to power I2x and e to power minus 2x. Then yx is equal to c1 cosine hyperbolic x plus c2 cosine hyperbolic x plus c3 cosine 2x plus c4 cosine of 2x. So then with this we have solved two examples on ODEs. Now let's move on to let's start dealing with optimization problems. Okay. So we'll start with the first problem, which is what is the cylinder of largest volume that can be placed inside the unit sphere? So which can be placed inside the unit sphere. So okay, we are given a sphere of radius 1 in which we have to place a cylinder, a right circular cylinder to be more precise, and that covers the largest volume. So let's fit it. We very well know that cylinder is defined by two parameters, radius and height. The radius is given by r cosine alpha. And before that, I must tell you that okay, we first express r and h in terms of capital R, but for that we need some angular measure. So what we do is we define alpha as the angle between the lines which is from the from the center of the upper surface of the cylinder, and we draw a line from there to somewhere where it intersects the where it just touches the boundary of the sphere, and another line which is which connects that particular point to the center of the sphere. This angle is called alpha, and from trigonometric relations we have the expressions as small r is equal to capital R cos alpha is equal to cosine alpha, and height we very well see that half of height is given by r sine alpha. So for the total height we need to have 2 r sine alpha, which is given by 2 sine alpha. Okay, the volume of cylinder here is V is given by pi r square h. Now we put the expressions of r and h in this expression. So this gives us pi cosine square alpha 2 into sine alpha 2 into sine alpha. Okay. Now we have cosine square alpha is equal to 1 minus sine square alpha. And what we do is we just express this in terms of sine, that we have an expression just in terms of sine. Now what we do is we need to find the necessary, and so essentially our problem has become an optimization problem in a single variable, for which the necessary condition to determine the extremum is given by dv by d alpha is equal to 0. This implies that 2 pi into cos alpha minus 3 sine square into cos alpha is equal to 0. This implies that cosine alpha 1 minus 3 sine square alpha is equal to 0. This implies that cosine alpha is equal to 0. This implies that alpha is either alpha is equal to pi by 2. But when we look clearly here, alpha is equal to pi by 2 simply makes r 0, which is not physically valid, because of which we just reject this conclusion. So we pick up the other conclusion, which is 1 minus 3 sine square alpha is equal to 0. And this gives us sine square alpha is equal to 1 by 3, for which we have sine alpha is equal to plus minus 1 by root 3. But again, h is given by 2 sine alpha, and obviously h is a is a dimension of length, is a denotes dimension of length, because of and that cannot be less than 0. Therefore, the only we can only pick 1 by root 3. Now what happen is, now let's take, and we have sine alpha star, which again, as I had mentioned before, that we denote star all the extremum points uh, by x star. So then, so that's why we have sine alpha star is equal to 1 by root 3. Now, now let's also determine whether at this point it's maxima or minima. So for that we resort to sufficient conditions. From the sufficient conditions, which is the double derivative of v with respect to alpha at alpha star has to be less than 0. And this means that alpha star leads to a local maxima. Then, which also happens to be global maxima in our case. Then, which means that volume is equal to, after putting all the expression for the value for sine alpha star, we have v max is equal to 4 by 3 root 3. And this solves our problem. Now let's pick up another for our problem. So the problem states that determine the extreme of the function f of xy is equal to 7x minus 8y plus 2xy minus x squared plus y cubed and their nature. Okay, so which means the questions asks us to find the extremum points first, and determine whether the points are local, is a local minimum or a local maximum. So let's first determine the extrema. So in this case, we have for determining the extrema, the necessary condition states that the first derivative of f with respect to x and y have to be 0. So this leads us to, so the first del f by del x is equal to 7 plus 2y minus 2x is equal to 0. And this implies that y is equal to x minus 7 by 2. Now, and the del f by del y is given by minus 8 plus 2x plus 3y squared is equal to 0. This means that minus 8 plus 2x plus 3, and then we substitute the value for y from the above equation is equal to 0. Then we expand it term by term, and finally we collate coefficients, all the terms in x square, x, and the constant to get the equation here as I have shown. This is a quadratic equation in x, and it should ideally have two roots. So using the standard quadratic formula, we have x is equal to 5 by 2 and 23 by 6. Putting these values in expression for y individually, one at a time, we get to, we get the corresponding y. It simply means that we have two extremal points, 5 by 2 minus 1 and 23 by 6, 1 by 3. The sufficient condition to states that, for the sufficient condition, mm, we first need to define or construct the Hessian matrix. So Hessian matrix given by del square by del x square, del square by del x del y, and del square by del y del x, and del square by del y square. Remember, you must recall that Hessian matrix is always symmetric in nature. For this case, we have del square by del x square is equal to minus 2, del square by del x del y is equal to 2, del square by del y del x is equal to 2, del square by del y square is equal to 6. Okay, at point 5 by 2 minus 1, we have h star is equal to minus 2, 2, 2 minus 6. Therefore, our trace here becomes minus 2 minus 6. And you must This, I mean, it said that we have to have eigenvalues. We need to determine the eigenvalues of H star. No, there are two ways. Either we denote we obtain the what do you call the eigenvalues, and this Bayesian matrix will have two eigenvalues. And so let's just find the trace and determinant. So since that these are easily obtainable, what we see is trace of H is negative. Trace is nothing but the sum of elements on the diagonal, which is -2, -6, which is less than 0. And the second thing is determinant of the Hessian, which is 2 minus 4, which is greater than 0. So as we know that determinant of a matrix is also the product of eigenvalues, since they are greater than 0 and the trace is less than 0. It simply means that both the eigenvalues are negative in nature. So negative eigenvalues mean that the extremum point 5/2 minus 1 is a local max. And for the other point, I will just construct the external the Hessian matrix, and I would urge you to determine whether there is a local minimum or local maximum by yourself. Take it as an exercise. Okay. The third problem here is to find the maximum of the functional. So we have a function fy is equal to 0 to 1 xy squared y prime cube dx. But this function only admits functions of the form y is equal to x to the power epsilon. Now take y is equal to x epsilon and find the first derivative, which is equal to epsilon x to the power epsilon minus 1. Substitute the expression in fy. Substitute the expression in fy, uh, and then we have f of y is equal to 0 to 1 x into x up to the power epsilon squared into epsilon x to the power epsilon minus 1 cubed dx. Now we expand each term, and then what we do is we collate all the exponents in x using the properties of something raised to the power x of the exponentials, so that we will just add up all the exponents here. So we have epsilon cubed x to the power 1 plus 2 epsilon plus 3 epsilon minus 3 into dx. Now epsilon cube being a scalar value and being our constant, we can just put it outside, and then we have 0 to 1 and x to the power 5 epsilon minus 2 into dx. And upon integrating it, we have this expression x to 5 epsilon minus 1 divided by 5 epsilon minus 1 from 0 to 1 is equal to epsilon cube into 1 by 5 epsilon minus 1. Now what we see here is our problem has become uh, a variable. I mean, our functional, the extremizing the function has reduced to uh, optimizing problem in a single variable. And so we just denote this as f of function as f of epsilon is equal to f of is equal to epsilon cube of epsilon minus 1. Now the necessary conditions begs us to equate the first derivative for the function to 0. This implies that 3 epsilon squared into 5 epsilon minus 1 minus epsilon cubed into 5 by 5 epsilon minus 1 squared is equal to 0. And this is follows from the differentiation rule of the functions in a fraction form. And so yeah, it's just d by dx of u by v is equal to u prime v minus uv prime by v squared. Okay. So what we do is now let's expand all the terms here, and then we have 15 epsilon cube minus 3 epsilon squared minus 5 epsilon squared is equal to 0. So this implies that 10 epsilon q minus 3 epsilon squared is equal to 0. This implies that epsilon squared 10 to the power epsilon minus 3 is equal to 0. With this implies that epsilon star is equal to 0 and 3 by 10. This follows from equating epsilon squared is equal to 0, 10 power epsilon 10 into epsilon minus 3 is equal to 0. Now, since we have just 2 points, and we very well know that the second derivative of f epsilon is going to be very tedious. So why don't we just evaluate function values themselves at both these extremum points? So f of epsilon star is equal to 0 is 0, and epsilon of f of epsilon star is equal to 3 by 10 gives us the value of 0.045. Our aim was to find the maximum of the function. So it's clearly it's a very apparent that f is maximum at epsilon star is equal to 3 by 10. So this implies that f of max is equal to 0.054. And if you want to just check it further, use and from the standard, no, from the sufficient conditions, then it can be seen that d squared f by d epsilon squared at epsilon star is equal to 0 is greater than 0, which signifies that as f is minimum at epsilon star is equal to 0, and d square f by second derivative of f with respect to epsilon is at epsilon star is equal to 3 by 10 is less than 0. So this implies that f is maximum at epsilon star is equal to 3 by 10. Okay. Now let's start solving problems in variational calculus. So in all this, for the next couple of next bunch of problems, we will have our functional in this standard form, I mean, it just for which the integrand is a function of y and the first derivative of y. Okay, so the first question asks us to determine the extremal of the functional, which is f of y is equal to 0 to over domain 0 to 2xy star plus y prime square dx, which is subject to fixed endpoint condition y0 is equal to 1, y of 2 is equal to 0. EL equations, the Euler equations gives us that d by dx of del f by del y prime minus del f by del y is equal to 0. Okay, so f is equal to xy prime plus fy prime square. This follows from by comparing our functional with the standard functional, which we are going to consider for the next bunch of problems. Now, then we have del f by del y prime is given by x plus 2y prime, and then taking d by dx of it, and also here we have del f by del y is equal to 0, since our integrand of the function doesn't contain uh, any term, doesn't have any term containing y. And so yeah, so which leads us to the equation 1 plus 2y double prime is equal to 0. So this implies that y double prime is equal to minus half. Now, to solve the differential equation, it being a second order differential equation, we just integrate it twice with respect to x. So y prime, upon integrating it the first time, we have y prime is equal to minus x to plus c1, and for integrating it again, we have y is equal to minus x squared by 4 plus c1x plus c2. And now to obtain the coefficients, so we have two constants here, c1 and c2. To to obtain the values for these constants, all that we need is to employ our boundary conditions, or which is also called here as endpoint condition. Now let's use the first condition, which is y of 0 is equal to 1. So this simply implies that C2, upon putting this, we have first term goes away, so which means minus x power 4 is 0. C1 of x is also 0. So we are only left with C2 is equal to 1. Using the second end condition, which is y2 is 0, this implies that then we have minus 4 by 4 plus 2 into C1, C2 is equal to 1. Okay, so we have minus 1 plus 2 C1 plus 1 is equal to 0. This implies that minus 1 plus 2 C1 is equal to 0, and then thereby implying that C1 is equal to 0. Therefore, y of x is equal to minus x squared by 4 plus y. Okay. Now let's move to solving the second problem, which is extremizing functional f of y is equal to 0 of pi by 4 y squared minus y prime squared dx with fixed end conditions, which are y of 0 is equal to 0 and y of pi by 4 is equal to root 2. Now we again compare our functional with the standard functional, which is given as um, and which is just given as f of y is equal to x1 to x2 f of x y prime dx. Now comparing this, comparing our this standard function with our functional, we have f of f is equal to y squared minus y prime squared. Now the corresponding Euler-Lagrange equations are d by dx of del f by del y prime minus del f by del y is equal to 0. This implies that dy by dx of minus 2y prime minus 2y is equal to 0. This further implies that we have minus 2y double prime minus 2y is equal to 0, and we can factor out minus 2 from the equation here, giving us y double prime plus y is equal to 0. Now, I must tell you that you must recall that we had solved a similar problem in the section on ODEs, and what we clearly see here is solution of this equation is of the form of a sin x plus b cosine x. Now, if you would like to know how we arrived at this, please go back to please look at the section here, and so that this differs from that problem just by not having 4. Yeah, so this is, and I'll go back again. Yeah, so we have this general expression is given by y of x is equal to a sine of x plus b cosine of x. Now let's utilize the first end condition here, which is y of 0 is equal to 0. This implies that b is 0. B0, the thing being that sine of 0 is x, sine of x at x is equal to 0 is 0, so which we only have b is equal to 0. And the second condition is y of pi by 4 is equal to root over 2. And this implies that a into sine pi by 4 is equal to root over 2. And then this implies that a into 1 by root 2 is equal to root 2. And then this implies that a is equal to 2. Therefore, y of x is equal to 2 sine of x. Okay. And this is our extremal, which also satisfies the given end conditions. Okay. Now the third question in this series is g of y. It happens to a function from a to b. So it's y squared plus y prime squared plus 2y power x dx. And we are asked to determine the general solution of the extremizer. So the integrand of the functional here is f of f is equal to y squared plus y prime squared plus 2y to the power x. Okay, now what we do is we first determine the Euler-Lagrange equations, which you by now you very much recall it. And from this equation, first we have to substitute the value of del f by del y prime. So del f by del y prime is given by 2y prime, and del f by del y is given by 2y plus 2 e to the power x. Upon substituting these expressions here, we have 2y prime plus 2y minus 2 to e to the power x is equal to 0. we can clearly see that we can factor out 2 from this equation here. So we are left with y double prime minus y minus e to power x is equal to 0. Okay, now let's just carefully observe this differential equation. Obviously, it's an ODE because it's the only independent variable is x, and when we look clearly, it is linear in the sense that all the terms contain uh, contain y raised to 1, which means there are no terms which contain product of y, or I mean product of higher powers of y. However, the one thing that distinguishes here is this equation is non-homogeneous in nature because of the presence of its power. So uh, theory of the techniques of solving an ODEs which are non-homogeneous is bit non-trivial in the sense that we have to express the general solution of this ODE as a sum of homogeneous the solution to homogeneous part and the sum and the particular solution of the ODE. Okay, so the first step for us here is to find the solution to the homogeneous part, which is yh double prime minus yh is equal to 0. Why we call it homogeneous? This because we have ignored we have just ignored e to the power x and took our forcing function to be 0, or in this case, the term not containing y to be 0. So this implies that again we can assume our function assume our solution to this problem as e to the power lambda x. Now putting the solution here, the assumed solution in this problem, we have lambda squared minus 1 into e to the power lambda of x is equal to 0. This implies that lambda is equal to plus minus 1. Okay, fine. And we have solved we have already we already know how to solve ODEs and also the solution to ODEs. So in this case, the solution to homogeneous part is C1 e to the power x plus C2 e to the power minus x. Fine. So we have obtained the homogeneous solution. Now our aim is to determine particular solution. So for particular solution, we have to assume a solution. Um, we have to assume a solution which tries to mimic the forcing function, or which in this case e to power x. However, there is a caveat here. What you see is the forcing function has a term which is the same as one of the homogeneous solution, which is e to power x. So which means that we cannot directly use it. You directly have a solution with to particular solution which contains only e to the power x. Rather, it must be a function which is linearly, or which doesn't so happen to be a what do you call to be a constant multiple of e to the power minus x. So what we do is we have taken our particular solution to be form of cx e to the power x. Now I won't be discussing why I have took this form, because this follows from the general solution technique for ODs, and also this is not what our aim in this lecture is. So if you would like, please you could consult any good book on ODs and you will get clear and very detailed explanation. So since this is not what we are supposed to be discussing here, that's why I have just taken the final result here. Okay, so why the assumed solution of particular solution is y p is equal to cx e to the power x, and then y prime of is equal to c to the power x plus cx e to the power. Now let me go to the next slide. Now I have copied the results from there, and I'm taken some part just to give you the overall process. And y prime of x is equal to cx plus c to the power x plus cx e to the power x, and yp double prime is c to the power x plus c to the power x plus cx e to the power x. And so we have 2c to the power x plus cx to the power x. Okay, so we substitute these expressions in our question to solve the particular integral, particular solution. So we have c to the power x, 2c to the power x plus cx is minus cx to the power x is equal to x. This implies that 2c e to the power x is equal to e to the power x. And this implies, and what we'll do is we'll just match the coefficients of e to the power x on both sides. So this gives us 2c is equal to 1. Therefore, c is equal to half. Hence, our particular solution is given by yp is equal to yp of x is equal to half of x e to the power x. We can easily very much, we'll just have to put the expressions for have homogeneous solution, particular solution to get the general solution of the externalizer. And this gives us y of x is equal to c1 e to the power x plus c2 into e to the power minus x plus half of x e to the power x. Okay. Now let's solve a fourth problem in this series. Okay. So here the question asks us to determine the extremal of the function for general f of x. So that and where f of x is general and our function happens to be defined over a domain A to B and f of x into 1 by root 1 by y prime 1 prime square into dx. Once we obtain the general expression, then we will have to find the normal expression when the for the case of f of x is equal to x. Okay. So just not to confuse you, let me take the integrand of the functional by let me represent it by a different variable which is g. So g is equal to f of x into root over 1 plus 1 times square. The Euler equation by now you will be at the peak of your time. This is d by dx of del g by dy prime minus del g by del y is equal to g. So del g by del y prime is given by 2y prime divided by 2 1 plus root y square into f of x. And since integrand doesn't contain any term, any just term containing just y, we are given del z by del y is equal to 0. This leads us to del z by 0. Okay. So this implies that dy by dx y prime over f x by 1 plus root 2 y prime square is equal to 0. Now, for a function to whose for a function for the derivative function to be 0, it's required. The only conclusion is that the function itself has to be a constant, and that's what it is here. That we have y prime of f of x divided by 1 plus y prime square is equal to constant, and I just denoted with c. Okay, so f of x. Now we have obtained the extremal of the function. Now let's pick up case for special case of f of x. Okay. So for the case when f of x is equal to x, this implies that y prime of x by root over 1 plus y prime square is equal to c. This implies that y prime of x is equal to c into 1 plus y prime square. This implies that y prime square into x square is equal to c square plus y prime squared. This implies that x square minus c square into y prime square is equal to c square. Now we can just rearrange all the terms containing y prime squared, and then yeah, we'll have an expression in y prime square is equal to c square by x square minus c. No, the question doesn't ask us to go any further, and so we stop here itself. That yeah, that our extremal will be of this form for the special case of f of x is equal to x. Okay, now let's start talking about generalized Euler-Lagrange equations. Let's solve some problems, and you very well recall from the review that for the functional for in such case the integrand of the functional does not only depend on y and its first derivatives, but it contains derivatives up to nth order of y. Okay, So the first question asks us to find the general form of extremal for the functional g of y is equal to 0 to pi by 2 y double prime squared minus y squared plus x squared. Fine. Okay. So the generalized EL equations and the integrand is denoted by f. Integrand for this functional gy. The general our equations you very well recall is and then we'll in this case n happens to be 2. So our general Lagrange equation is given by 1 minus 1 squared divided by d square by dx square into del f by del y double plus minus 1 to the power 1 dy by d by dx of del f by del y plus del f by del y is equal to 0. So yeah, we'll expand it, and then what we do is we put and what we do is let's substitute the uh, expressions for del f by del y prime double prime and del f by del y prime and del f. Now del f by del y double prime happens to be 2 into 2 into y double prime. So, and similarly del f but since our since f does not contain any term in y prime, so del f del y prime is 0, and del f by del y is nothing but minus 2 of. Okay, so we have our expression. I mean, this leads us to 2y 2 into 4 derivative of y minus 2 into y is equal to 0. Again, we can just factor out 2, giving us y to the of the 4 derivative of y minus y is equal to 0. The general solution is y of x is equal to a cosine hyperbolic x plus b sine hyperbolic x plus c cosine hyperbolic n d. You very well recall this solution, right? From the review part, from the solution to ODs, we had solved a similar problem. We had solved a very similar problem here. Yeah, just that it has 16 here, and we don't. That's the only difference between this equation and the one we currently have here. Okay, and the general solution is y of x is equal to a cosine hyperbolic x plus b sine hyperbolic x plus c cosine x plus d sine x. Okay, now let me present to you some problems, some real life problems or problems in engineering. Uh, so the first problem in this is that of a problem in structural mechanics. I'm sure you must be aware, if you have a background in mechanics, that the most widely model to study beams is widely used model is Euler-Bernoulli beam. And so our aim here is to determine the, the deflection which minimizes deflection W, which minimizes this energy function. So the first here, this contains potential energy or something known as, or in this case, strain energy. The second is work due to external loading. Okay, let me go term by term here. E is the Young's modulus, I is our moment of area, moment of inertia. W double prime is the double derivative of deflection with respect to x. Q happens to be our loading, distributed loading. And, our beam is considered to be of unit length. I have just present a schematic here on the right hand side here that we have a beam of unit length and W determine the deflection of the center line, and this beam is subjected to a distributed loading Q. Okay. Now what we see here is that the functional here contains terms which are terms in y with order of derivative more than one. So this asks us to uh, deploy tools from generalized or the generalized Lagrange equations. And to obtain the general Lagrange equations, we define the integral as this. We have this integral here, half of e I w double prime square minus qy qw, and then we go through a similar process as in the previous case. It d square by dx square del y by del y. Then likewise, And then we have d square by dx square ey w double prime minus, which is the function. The function doesn't contain any term in w prime. We'll just take del y by del y prime is equal. It just leads to del y by del y prime is equal to 0. And then we have minus q is equal to 0. So this implies that del square del y square ei w double prime minus q is equal to 0. Okay. So we have obtained the extremizer of the energy function for order but not beam. Now the second part asks us second part of the question asks us to determine a general solution when ei is constant, q is equal to q naught, and q naught also is a constant. So what happens is in this case, when we take a look in this expression here, we have we can since ey is constant, we can split out of the differential operator so that we have eiw for derivative w minus q naught is equal to 0. This implies that for derivative of w is equal to q naught by ei. Now this is a question. Sorry, this is the differential equation of where the principal term is fourth order in w. So we need to integrate this equation 4 times. So first we'll integrate with respect to y, and this gives us, I mean with respect to x, this will give us d3w by dx, right? d2 dx to the power 3 is equal to q naught x by ei plus some constant c1. Integrating it again results in q naught x squared by 2 ei plus c1 of x plus c plus c2. So by now we have two constants. Let's integrate it once more. And this gives us q naught x cubed by 6 ei plus 1x squared by 2 plus c2 of x plus c3. And we'll have integrate once more, and this will give us the general expression for the deflection of the order per order beam. And this is q naught x to the power 4 by 24 ei plus c1 x to the power cube by 6 plus c2 x squared by 2 plus c3 x plus c4. Okay. So by now, yeah, we have derived determined the general solution of the problem when our EI is constant and subjected to a constant loading Q naught. Okay. Now let me let me solve one problem in in structural mechanics, and not in structural environment, in structural dynamics actually. This is a problem of mass which is attached to a spring. That has the one end of the spring is attached to to a fixed wall, and one end and the other end is attached to a mass which oscillates on a frictionless surface. The displacement is given by x, which happens to a function of time. T here denotes time. Now you must recall, you may recall that uh, this is a schematic of a very simple harmonic oscillator. Okay, now to describe the motion, at first and our aim is to determine the equations of motion. So we'll start with, let's first construct the function here. So the function here is to minimize or to extremize this particular term here from t1 t2 to L of dx and x dot, and x dot you must recall that we often tend to use dot to denote differentiation with respect to time. So this particular thing can be stated as that we are trying to extremize the action of the motion of this mass here. And now this L which we also call as Lagrangian is expressed as T minus V. T here is the kinetic energy, V is the potential energy of the system. Now you know that kinetic energy is defined for a mass, and mass here is denoted by m, and the kinetic energy is defined as half into mass into velocity square, and velocity is nothing but rate of change of displacement. So we have t is equal to half of m dot x dot squared, and v here denotes potential energy, and the potential energy, the only potential energy in this case right here is, since our mass is oscillating on a horizontal surface, the only potential energy is here is the strain energy in the spring. Now, due to the motion of M, and, the extension in spring happens to be x. So which gives us the strain energy in the spring to be half of kx squared. Okay. After putting this both these expressions for t and v in our in our Lagrangian, we have L is equal to half mx dot squared minus half of kx squared. The Euler-Lagrange equations are is d by dt of del x del L by del x dot minus del L by del x is equal to 0. This implies that dy by dt of mx dot minus kx is equal to 0. Okay. Okay. We have dy by dt of mx dot minus kx is equal to 0. And this gives us mx, and since m is a constant, we have mx double dot plus kx is equal to 0. This you recall very well that it is the equation for a simple harmonic oscillator. Okay. Now let me just extend this problem further. Now this here we have a vibrating system consisting of two masses m1 and m2, and here we have attached two springs k1 and k2. The individual displacement of the masses m1 and m2 are given by x1 and x2 respectively. Following the similar procedure in the previous problem, we construct a functional from functional, and it minimizes something we call as action of the sum. But okay, let's just skip that part. Let me just tell that okay, we have constructed this functional, and then the Lagrangian is defined as T minus V. T is the kinetic energy, and the total kinetic energy system is nothing but total kinetic energy is nothing but half of m into velocity of 1 squared plus half of m into velocity of squared, and then the net kinetic potential energy is half of k1 x1 squared plus half of k2 x1 minus x2 squared. Now I will ask that okay, fine. The strain energy is the sum of strain energies in each of the springs. So for the first spring, it is the extension happens, one end is attached to the wall, so the extension is just x1. However, for the second spring, what we see is one end is connected to mass 1, whose displacement is given by x1, and the other end is connected to another mass whose displacement is x2. The net extension is x1 minus x2 squared, x1 minus x2. So the energy, as you very well know, that energy stored in a spring is solely due to the extension, change in length from the original state of the spring. So the net extension is x1 minus x2 squared. Fine. Now what we do is, now let's go on to derive our Euler-Lagrange equations. So the first Euler-Lagrange equation is dy by dt of del x del L by del x dot del x1 dot minus del L by del x1 is equal to 0. This implies the derivative of m1 x1 dot minus, and the rest of our terms minus of x1 minus k2 x1 minus x2. And since m1 is a constant, we can take it out of this differential operator, and then we have m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equal to 0. The second Euler-Lagrange equation is dy by dt of del L by del x2 dot minus del L by del x2 is equal to 0. This implies that we have dy by dt del L by del x2 dot is nothing but m2 x2 dot, and del L by del x2 is minus k2 by x1 minus x2 into minus 1. Again, we have m2 is also constant, so we have m2 into x2 double dot plus k2 into x2 minus x1 is equal to 0. Okay, so we have opened two equations. I'll put it in. I have put both of them in one place. Now There is an elegant way of putting this equation, and it happens to be something that we can just form a matrix. So the matrix, we can put it elegantly in a matrix form, so that we have M1, M2 forming a diagonal matrix, and then the rate of change velocity, which is acceleration for both x1 and x2, both the degrees of freedom plus k1 plus k, and then we have this. This is known as mass matrix. Mass matrix of the system. This is known as stiffness matrix of the system. And x1, x2 is equal to 0, 0. Yeah, so this is what I had planned to teach today, and then to review all the problems. And I hope that this will help you to solve your the assignment for week 1 and 2. So yeah, and I don't see many persons here. There is just one attendee. So please let me know if you have any doubts. And okay, so please let me know if you have any doubts. And this was supposed to be just the introductory lecture and tutorial session, and we will be discussing our problems further in more advanced problems in the upcoming session on 14th Feb. So yeah, so should we wait for some more time, or just quit the discussion, because I don't find any more people joining the meeting. Yeah. So should we wait for more people to join in? Because I mean, I don't see anyone joining. Or quit or okay. I see. So which means, yeah, we can. So I think it's an ideal time that we just quit the meeting and continue the conversation next time. So is it okay? Um, okay then, yeah. So what we'll do is we'll continue our next discussion from here, and we'll be discussing. Please let me know if you have any other problems, and yeah. So with this, I'm just closing our discussion here. So let me just stop the recording.